All right, so this is a tutorial for how to use Nastran Simcenter to set up some basic FEA. My name is Yash, and I'm on Formula Racing at UC Davis. So right here we have an upright that goes in our wheel package, and we're just going to go through the process of using Nastran and setting up semi-correct or correct boundary conditions. So let's get started. So this is the part that we're going to use for the simulation. Um, I've imported it as a step file from SolidWorks, and the way I did that was just file, import, and then scroll down to step, whichever step you used, and then you can just go through the process. You can play around with these settings, but most of them usually work. Um, yeah. Okay, so this is the upright. And so the very first step is if you need to do any pre-processing to just like maybe define some surfaces or something, you can do that. But since this tutorial is kind of basic, we don't have to go through that step. Everything's kind of ready. So the very first step is you want to go here, go to File, New, and then you go to the Simulation tab. And to do simulations in NX, Simcenter, Nastran, there are two files, and this is probably one of the biggest distinctions from other softwares. Like most other softwares like SolidWorks or even ANSYS, I guess, they just have one file that has the meshing and the like boundary condition input and everything in one single file. But for NX, there's two files, FEM and SIM, so finite element modeling and simulation. So the very first one we're going to create is the FEM model, and we can name it like upright tutorial FEM, and then save it wherever. I'm going to put it on the desktop. Okay, and then on to zoom things in the way. Then hit OK. So now it's going to create the FEM model and then pull up some options. It pulls these options up every time you create a new FEM. So these are the options, and everything is kind of just set for you already. I guess one of the biggest things you can do is choose whether or not you want to create an idealized part. So what an idealized part is, it's the part that the FEM and SIM files are going to use for modeling or for the simulation. So you can make changes to the idealized part without making changes to the original part. So the idealized part, you can just like screw around, maybe make some like different shapes or just test a lot of different things with your model, and just kind of go through rapid iteration to see how it changes your simulation results. But for this tutorial, we're just not going to create one. And this is another way to do it too. If you want to just straight up make changes to your original part, those changes will also be reflected and updated in your sim and fem files. And one of the big reasons that Simcenter Nastran might be a better alternative than CMAP or other similar softwares is that, similar to SolidWorks, it can just update design changes throughout the entire FEM and SIM files. So if you make a change to your original part, it'll be reflected in your final simulation after you just update everything. So let's go ahead, and now we are in the FEM model or FEM file. And the very first thing that you're going to do is find mesh collector. And just a note, if you can't find anything ever in Siemens NX, then just search like mesh collector, click enter, and it'll just like show you where it is, or you can even click that to enter the file or the option. So we're going to go to mesh collector, and this is where we define the material or the different materials we want in our overall file. So say we have multiple different materials, maybe an assembly or something that we're simulating. So you would make multiple mesh collectors for each type of material. So you can even choose like 2D, thin shell, maybe a laminate. You can define your laminate right here. That's for some of the carbon fiber or composite simulations if you ever want to do that. But for this one, it's a 3D part, solid. We'll just go P solid, and then we're going to create a physical solid property. So we can just call it whatever we want. I'll just call it aluminum. Let's see, material. We can choose our material with this button. Let's just do 6061 aluminum. It's isotropic. If you want to create your own material, you can choose the type and then input your material properties right here. But right now we're just going to choose the built-in 6061. Hit OK. Coordinate systems and everything else looks good. Hit OK. So it'll bring you back to the original mesh collector file manager or opener, whatever. And you'll see the one you created is right here, aluminum. And just to go through the process again, hit mesh collector, then define the type of mesh collector. You can make your own solid property with this button here, or edit or open manager, and then just hit OK. And now you'll see on the left, we have 3D collectors, and you'll see the solid one that we just created is right there. Now the next step is going to be to create a 3D tetrahedral mesh. So there's multiple types, see Tetra 4 or 10. These are the most commonly used. I believe C Tetra 10 just has more nodes for each mesh element. We can go with either. I'll just go with 4 right now. And then I like to just click this lightning bolt, and it'll just tell you that's a good size for your mesh. So 0.06 is fine, so I'll just round down to 0.05. And then you can mess around with the different meshing options to generate a better mesh. I'll just leave everything as default for now. And then for most of the times you're going to open this, or the first time you open this menu, this button is going to be checked. So we're going to want to uncheck it and choose the mesh collector that we just made. So if you don't do that, it'll just make its own mesh collector. So we made it for the purpose of making the mesh, so we're going to use that. So solid 1 is selected. And the last thing is you want to just select the body that you want to mesh. So after doing that, you hit OK. It's going to be meshing. You can see the progress on the bottom left. And so basically what a mesh collector is it's just like, it's kind of what its name means, just a place for your mesh to be collected. It's different than other softwares in that the mesh collector includes the material, and then the mesh is kind of goes into these collectors that have materials already. So okay, you'll see the mesh is done already. You zoom in, it's pretty fine, and it'll be fine for our purposes. I could even go coarser if we want to make the simulation go faster. I'm going to do that actually. Go 0.1. So this one should mesh a lot faster because it's larger element sizes. Okay, so it's a lot coarser, so it'll simulate faster. You're going to want to make a finer mesh towards the end of your process, after you've found that your boundary conditions and everything are working as expected. Then it's a good idea to go through with the finer mesh for your last simulation. So yeah, you'll see 3D collectors. This is the collector we made, and this is the mesh that we made to go into that collector. So now everything's mostly done with this, the FEM model, or the FEM file. Now we're going to go through and create the sim file. So the same thing, go to File, New, and then double click, or maybe name your file first, Upright Tutorial Sim. and then just double click that. So now it's going to open up the sim file prompt. And you can get kind of technical here. We'll try to keep it simple. So you just choose the FEM file to go along with this simulation. So all of the upright tutorial FEM stuff from the previous file we were working in will be updated into this sim file. So that's it for this menu. And then this next menu that's going to come right here, this is where you can really get custom, or where you can customize a lot of different aspects. We'll go over some of them. You can always learn more from the Nastran user guide, or just go through and click through a bunch of different menus. So the solver we're going to use is Simcenter Nastran. It's a structural analysis. There's a lot of different solution types, but for the general FEA, we can just do global constraints. And then you can go down to case control. And then you see parameters right here. You can go into this menu with the button next to parameters, and there's a bunch of different settings that you can play around with. I'll show you two that I was able to learn recently. First one is bailout. And what this does is basically force solves your simulation if it's set to -1. So this could be cool for just testing how your boundary conditions are looking, seeing maybe where they go wrong, just like forcing this solution to be solved. But you just have to make sure you change it back to 0 before your final simulation solve. That's one setting that I was able to learn. The other one is an S-T SR comp, so strength ratio comp. So this is used for laminates. So it'll tell you the ply strength ratio, but this isn't a laminate, so we can just leave it as no. So the only thing we changed is bailout -1. So it'll just solve anything you give it, which is kind of cool. And then other things you can do, we can go to output requests right here, also under case control, and then hit that wrench. And these are the different things that'll come up in your post-processing after you've solved your simulation. So maybe one thing that we'd want is strain. We want to solve for strain. So just enable strain request, and it'll plot a contour plot once everything's solved. So there's a lot of different things, outputs you can tell Nastran to give you. You can play around with that too. So those are the main things I've gotten familiar with in when creating your sim file. These are some settings. And then so you can just hit OK. And just to show you how to go back to that menu, if you want to maybe undo bailout or change some other settings, you just on the left-hand side, scroll down to solution 1, the one you just created, then hit edit. And it's the same menu again. And okay, so before we go any further, I'll just show you how to toggle between your part file, your FEM file, and your sim file. So there's multiple ways to do that. One is right here with the simulation file view. So you can just double click FEM, and even part. And like in the part, you'll notice that it's not the normal modeling like toolbar you're used to. So to go to there, you go to applications, then modeling. And now you have everything back to normal. And if you want to go back into FEM or sim, you click window up here in simulation. So yeah, this is one way down here with the simulation file view. Another way is window. And the final way is right here in your left-hand menu. You can just double click FEM or go back to sim. And you can see everything you created in your FEM is right here in the FEM drop-down menu within the sim file. So your whole geometry, we didn't do any mesh control, your 3D mesh, you can show and hide it as you desire. And so now we're getting close to having a complete simulation. So I'll just show you how to just apply basic constraints, and then I'll show you an upright with correct boundary conditions. And I guess a cool exercise would be to try to get to that same result as me, without me showing you exactly how to do it. But okay, so you can go either up here, load type, constraint type, or you can go on the left-hand menu. We have constraint container, load container, and create a new constraint. I like doing a user-defined constraint. So it'll pull up this big menu. You can say, okay, maybe I want these holes to be fixed. Let me unhide the polygon or the original geometry, not just the mesh, so I can select some of these corners. Okay, and then maybe this one too. This one. So okay, I just selected some random holes, and then I'm just gonna fix all degrees of freedom. So 1, 2, 3 is X, Y, Z translation, and 4, 5, 6 is X, Y, Z rotation. So if you only want some degrees of freedom fixed and not others, you just put them as free if you don't want it fixed. And yeah, so hit OK. You'll see this blue means that there's a fixture there. And then let's add a load. So you can do a lot of different loads. We'll just go basic with force. Then let's say we want force on this half of the upright main big hole. So let's just set it to newtons, do 5,000 newtons. And we can choose multiple ways to define the direction, of the force. I usually do a long vector, and then you can choose which vector through this drop-down menu. Say we want it in the negative x direction, so it'll put a force towards the left of the screen. There are other ways to define vectors too. There's this whole vector dialog that a bunch of ways to define your vector. But yeah, we'll just go negative x direction for now. And then geometric distribution is just like 5,000 newtons along the entire region total, not total per object. So hit OK, and you'll see these arrows showing the force I just made. And lastly, you just hit solve. Or if you have multiple solutions, right click it, and then look for solve, hit solve. So hit OK, we want to solve it. You can also do other stuff, but most likely you want to solve it, hit OK. Now it'll pull up some information. So it just shows you what's going on. This is a job monitor, which will just tell you that the job you just submitted is in progress. And then in a bit, you're going to see a Nastran solver come up. There it is, solution monitor. So this is kind of real time what's going on. You can review all these messages after it's solved. It'll let you do that. So yeah, this will take a little bit, not that long. So solution is completed. Do you want to review the messages? Yes or no, you can choose. I usually just scroll through. For while it's solving, I look if I kind of just stare at it if it's not a super fine mesh, because it'll just solve quickly, and see if any errors come up, then you can just click cancel. You'll see this is completed, the job you submitted. And now yet another, I guess, file. It's not really a file because it's within Sim, but another place you have to go to see your results is within the solution one, double click results, and it'll pull up another left-hand thing, and you're gonna hit structural and see the simulation that just solved. And I'll go through a few of the post-processing things you can do. It's kind of intuitive to go through yourself, but some things are not as obvious. So just, yeah, you can double click this is currently displacement in inches. Max displacement was 0.0048. You can also look at rotation, stress, strain, because remember we activated strain. So it wouldn't show these two unless we went to that output request like place in the solution one like settings. So there's that and other things as well. And if you want to dive deeper, maybe see stress in like certain directions, and it'll show you that too, or maybe displacement in like the X direction only, it can show you that. So yeah, you can just double click on anything and it'll just pull up a contour plot. And so one cool thing I like to do is just animate. So you can either click the play button here or go into animate and then hit the play button. The same thing. You can see the simulation you just did. Notice how these holes are fixed like we told it to, and there's force in the negative X direction going as we see. Okay, and then some other nice things are banded displays are usually nice because it'll show like concentrated stress, unlike when it's smooth. And then you can edit post view if you'd like. In here, there's a lot of different settings. You'll notice right now it's like super deformed, even though it only says 0.0002 deformation, inches deformation. That's because it's the 10% of, so everything's like 10 times more visually. So you can just change it to 1 and then hit OK. And this is like actual deformation with your load conditions. Hold on, I think my mouse died. Okay, should work now. So other things you can do, you can mess around with the mins and maxes of your legend bar. You can say maybe I want it from 0 to like 5, and then you can click override value, click customize, look at different colors. Maybe I want, instead of blue there, I want it to be like pink or something. You can do that. So then you hit OK. And now since we changed it to 5, everything's kind of low in blue. I don't know why it didn't become pink. That's something I can spend some more time on, but it's fine. And another cool thing is for factor of safety, you go into result, or actually first you go click this button, result variables, and then you want to create a new variable. Let's call it von Mises stress. Let's see. We'll go to the result type is stress, and component we'll say von Mises. I haven't really messed around with these options too much. I'm sure there's documentation somewhere, and then just hit OK. So what this does is it creates a variable for all the different like values across your contour plot that can be used as a variable. So the variable we made was for von Mises stress, which is right here. There it is. You'll see the color bar is still kind of messed up, but yeah, you'll see stress there. Okay. So now after we've gone into result variables, we'll go into result probes. And we're gonna make a formula. So I guess I just know because I looked it up recently that 240 megapascals is the yield strength of aluminum 6061. So what we're gonna do is do 240 megapascals. So 1, 2. So I think that's the right amount of zeros, and then divided by the von Mises stress, the variable you just made. So it's gonna make a contour plot for factor of safety, because this is the factor of safety formula, yield strength over von Mises. And then you're going to want to create output and then hit OK. And so you'll notice that the units are kind of messed up. And the reason for that is because I didn't really keep it consistent. So what would have been a better thing to do is look up units. I can never find where it is. So I just search it in the bar, hit units manager, and then just make everything metric. And close this. Then we'll go back to our result probe and do the same thing. And now you'll see the units is inverse Pascal. That's because there's no unit to the value I put, but then this VM stress is Pascal's. But since we know this is Pascal's, it's factor of safety, so we're good. Now you create output and all your values should be nice and good. So you'll see the minimum factor of safety, 3.12. So it is over-designed for the weird boundary conditions we made. But okay, one, I guess, downside of result probes is you can't really change the error bars, like the edit post view, or not the error bar, the color bars. Edit post view doesn't really update for it when it's a result probe, but that's just one downside. Instead, you can go ahead and create annotations. I believe this is how. Go to this A, and then let's say I want to know, one second. So yeah, let's say I want to know the factor of safety of this element. You can select multiple, but let's say I really want to know it for that element. So we go through, just hit OK, and it'll tell you the factor of safety for this single element, this triangle, is 10.3616. So yeah, that's one way to get around the lack of flexibility with the color bar, but yeah. And to go back to a different result, you can just double click or pull that up. And so, okay, we got to this results menu with all these results settings, but how do we go back to our sim, like our normal sim place? So you can go back to home here. You can even click return to home and you'll be brought back to everything. And another way to do that, just toggle between home and the non-home results or whatever, is just this bar. So post-processing navigator and simulation navigator. So that's most of the tutorial. I guess one other thing to mention before I show you the final simulation is that the way to apply remote loads and also even moments is through 1D connections. And this is a little unintuitive, but I'll show you how it works. So let's go back to the SEM file. And let's say I want to apply a force from this point, a remote load from this point onto this surface right here. Which is actually something I did for the final simulation. So there's a couple of different steps you have to go through. The first one, we'll go to nodes and elements up here, and let's create a node at this coordinate system. So to do that, everything's just 0, 0, 0. You can just hit OK, and it'll make a node. And then after that, you're going to go to 1D connection, select that node as a source. Then as a target, we want to select all the nodes on this face, because that's where we want to apply the remote load. So the fast way to do that is make a selection filter, I guess no selection filter, and then click related nodes. Then if you just click it, it'll select everything there. So, which is pretty neat. It goes fast that way. So you hit OK, And then the type of connection, we want to make sure we change it to an RBE2. So this is a rigid body element of type 2. There's also type 3. And it's different than other programs in the way you apply different types of loads. So with RBE2, it's a rigid body element which kind of just defines how the force will be transmitted along it or kind of through the element. And so hit OK, and you'll see it makes a bunch of rigid body elements from this coordinate system node to the all the nodes on that face we wanted. And so it actually makes like actual rigid body elements. So these are lines that carry load. And the next thing we want to do in the FEM file is we're going to go to 1D collectors. So this is the one you just created. And we want to edit mesh associated data. And so now we're going to constrain the way that load can be transmitted across these rigid body elements. So for this example, I'm going to transmit a load from this point to this, like this thing, in the Y direction. So we don't want any rotation. So XYZ rotation can be turned off. And we don't want translation in the X or the Z, only in the Y direction. Then you hit OK, and now load can only be transmitted across the Y direction for these rigid body elements. And so after that's all ready to go, you go back to your simulation file. So double click sim. And then you'll see the 1D collector rigid body element that you just created is right there. You can toggle it on or off through the same menu. And now let's apply a load to another force. And you can just select the rigid body elements that you just created and apply maybe a 2500 Newton load in the negative Y direction. So it'll apply it in that vector. So from here to all of this, and then geometric distribution, everything looks good, hit OK. So now, I guess, yeah, another cool thing to explain at this moment would be that you'll have constraint and load containers that can be used for any of your solutions that you end up creating. And then within each solution, there are constraints and loads that you've added to the solution. So by default, it just throws in the constraints and loads from the container into these, what are they called, properties. But you can say, okay, maybe I don't want the first force I created in this solution. Maybe I want it in another one. Then you click remove, and that'll just remove it from the solution, but it'll still be in the load. It's just inactive because it's not being used. But yeah, that's just another, I guess, side point. But yeah, let's just simulate this load with the same inaccurate constraints. And let's go for it. Let's also turn bailout off. Let's remember to do that. Now it won't just force solve, it'll solve only if it is solvable. Now everything's good to go, hit OK, and then just hit solve. The last simulation took like 10 seconds. I don't expect this to take any different time than that, so you can just wait. In progress, information, and then the solution monitor. It's all done, nice. So hit OK or yes. You can close everything, completed, and double click results, structural, and there you go. So let's animate that. Let's see how it looks. So it's applying force from this point onto this point, or these points. It looks like we applied it correctly. We know that the constraints are not correct, but the constraints that we did put look like they worked as expected. So that's a good sign. All right, so now that's pretty much it for the basic walkthrough of MX. And I'll just show you the completed simulation for an upright with hopefully accurate boundary conditions. All right. I think this is the file. Yeah, so I'll go through the boundary conditions first and then show you the results. So there are, you can just open them. So solution one, let's go through the constraints. There's two types of all these holes. The 1, 2, 3, 4 holes are fixed in every direction except the Z in translation. Then there's two holes up here that are fixed in every direction. Then we have a bunch of loads. Let's go through the moment first. So let me open up the 1D collectors. I will go one by one. Okay, so the moment load. So we created 1D collectors in the same way from here to all these nodes within the hole. And then we applied a moment load. So not force like we've been doing, but moment, which is right there. We applied it to those rigid body elements, and these elements are constrained. I believe they're constrained in everything except Z translation and Y rotation. Yeah, I think that's correct. So it's just 550 Newton meters along these rigid body elements. And the vector along which it is applied is the negative Y direction. It's kind of hard to see, but that's the vector it's applied on. Okay, and then there's several normal loads. Let me pull up those rigid body elements. Okay, I guess before we go to the normal loads, there's loads in the Y direction, pretty much the exact same as I showed in the tutorial. So these loads are on this like disk, and I'll just show you the conditions. So 2800 newtons in that direction, and then we have normal loads, which are using these rigid body elements. So there's two, kind of hard to see. The one is from this point to this part, and then the other is from that point to this part of the upright. So how does that look? The way it worked was we had to keep it separate. Like each rigid body element group, I couldn't select both of them into one force. I had to do it in two separate forces. So the boundary condition is actually 2000 newtons along both of these faces, but I just split it up as 1000 in this region and 1000 in this region. So that's normal Z1, Z2, those are that. And then braking load is the same exact, using the same rigid body element as a normal force, except in the negative X direction, which is that arrow right there. And this was 2400 newtons total, so we did 1200 on both of these regions separately. So those are the conditions. And just, I guess, a note that I didn't clarify each time. Within each rigid body element, the mesh associated data had different degrees of freedom selected for each different type of rigid body element. So it just varies based on the type of load you want to apply. So that's just something to keep in mind. So this is all set up and I've already solved it. So we'll go to the result and just show you the displacement. I think it's, let me make it 10 times. One second, let me update this to be 10%. Okay, so let's just animate it. So that's what it looks like. So we have force going in, force going that, or force going this way, right, and then force going up, and then moment from these points, as we described earlier. But yeah, so that is your simulation. And I guess one thing that I did while setting it up was I didn't just go ahead and apply all these forces and then solve and call it good. I kind of isolated each force. So basically I did one force at a time, solved it, saw how it looked, made sure that everything was as expected, and then went on, did all these different forces separately, not together, made sure they looked reasonable, and then combined them all, and then solved. So yeah, there's a lot of different ways to do it, but that's the basic workflow. So I hope you were able to learn how to go between the different files, the SEM, SIM part, idealized part. I hope you're able to learn about how to do your mesh using mesh collectors, then 3D meshes, then 1D connections, which were the RBE elements. And then in the sim model, we learned how to add constraints and loads using the RBE element. So yeah, hope you were able to learn all of that. And thank you for watching.